Dilution of a solution. Those words are too similar. Many solutions that we use in the lab are prepared by diluting a more concentrated solution, and those concentrated solutions are called stock solutions. The room where we store the chemicals is called the stock room, and we have stock solutions in there, and if we need, say, a 0.1 molar sodium hydroxide solution, instead of weighing out sodium hydroxide and making this whole solution, we can go and use the 1 molar or 5 molar stock solution that's just sitting there and make the solution that we need. It's just much easier. These stock solutions, the more concentrated solutions, you could think of them a little bit like you're keeping the frozen concentrated orange juice in the freezer, right? And then when you want orange juice, you take the can out and you add water to it and you make orange juice that's diluted and drinkable. Why don't we freeze gallons of regular orange juice? Would that take up a lot of space in your freezer? Yeah. By taking the water out and concentrating it, now you've got that whole gallon in a little can. Well, it's half a gallon. You've got it in a little can. It's easier to bring home from the store. It costs less for them to ship all over the place, right? It's convenient. Chemists use stock solutions for the same reason. It's convenient. So an important idea about dilution is this. The amount of solute does not change during dilution. So let's think about making orange juice. You get out the big pitcher and you pull out the can of orange juice concentrate. There's a certain amount of orange goodness in that can, right? And when you empty the can into the pitcher, do you gain orange goodness? Do you lose orange goodness? No. You get all of the orange goodness from the can into the pitcher. And then you add water. When you add water, does that change how much orange goodness is in the pitcher? No. It just expands the volume. The amount of solute doesn't change. The amount of solution changes. The concentration of the solution changes. But the amount of dissolved solute stays the same. So the amount of solvent increases. The volume of the solution increases, the molarity, the concentration of the solution decreases, but the amount of solute stays the same. So let's think about preparing 2 liters of 0.3 molar potassium hydroxide from a 5 molar potassium hydroxide stock solution. And first we're going to use the conceptual approach, and then we're going to use an approach involving algebra. So here I've got my stock solution. This is 5 moles per liter sodium hydroxide. And I'm going to take some of that and I'm going to put it in my beaker over here. And the volume here is 2 liters. And I want the concentration to be 0.3 moles per liter sodium hydroxide. Well, how much of this do I add? Oops, I touched that with my wrist and I did that. Interesting. Pardon me?
You are a slight source of electricity.
Apparently I am, yes. And I cause buzzing when I touch things.
I do the same thing with my fridge.
Oh, yeah? You make your fridge buzz?
Yeah, it's stainless steel. So
Oh, interesting.
It's really high pitched and really
Does that keep you away from the fridge? No, not enough, not annoying enough. Well, so here we have this concentrated solution. What we need to do is we need to take some of this and put it in this big beaker and add water to it. Because this is 5 moles per liter. This is 0.3 moles per liter. What did I tell you about the amount of solute? It's going to stay the same. What's the amount of solute that I want in this beaker? Could we figure that out? Moles of sodium hydroxide? I've got a volume, and I've got a unit factor here that relates moles to liters. So 2.0 liters, that's an L, and I want to know how many moles of sodium hydroxide do I need. So I need 0.3 moles for every liter. So that comes out to 0.6, right? So in this beaker, I want 0.6 moles of sodium hydroxide. And then I'm going to add enough water to give me this volume. Does that make sense? A little bit? Well, how much of this solution do I need to measure out to get 0.6 moles? This concentration relates moles and liters. So if I know the moles, I can find the liters. So I'm going to go over here. I'm going to say, well, I need 0.6 moles of sodium hydroxide. And I'm going to use that molarity as a conversion factor. I'm going to put moles of sodium hydroxide on the bottom and liters on top because I want these guys to cancel out. Well, it's 5 moles for every 1 liter. So I've got 0.6 divided by 5, 0.12. So that's 0.12 liters. If I take 0.12 liters of this concentrated solution and put it into my beaker and add water so that the volume is 2 liters, then I will have my 0.3 moles per liter sodium hydroxide solution. Yes? Yeah, it is. Thank you. You're right. It is potassium hydroxide. But now it's sodium hydroxide. Because that's easier than changing all the sodiums. Oh, I got to change the other one too. Okay. Yeah, that's what my husband calls a brain fart. It's just like a hiccup in my brain. Thank you. So I'm sensing that most of you are not liking this approach. Would that be correct? You're like, I don't know about this. Where are you going? Is that kind of how you're feeling? Okay, so let's look at it a different way. Algebra. Now, normally I don't think you are big fans of algebra, but I think you'll find this algebra okay. Here's an equation. M1 V1 equals M2 V2. This works because what is molarity times volume? Molarity has units of moles per liter, right? And volume with units of liters would get us moles. If you take the concentration of a solution in moles per liter and you multiply by the volume in liters, you get the moles of solute. The moles of solute in the first solution equal the moles of solute in the second solution. That's why this equation works. So this requires, we're going to do the same problem here. This requires that we identify what's M1, what's V1, what's M2, what's V2, what are we looking for? So one approach to this is to make a little table. So we're going to have 1s and 2s, and we're going to have capital M's and capital V's. And then we're going to look at this. It does not matter which solution you call 1 and which solution you call 2. It doesn't matter. So here we've got 2 liters of 0.3 molar. Do you see that those two numbers go together? They are referring to the same solution, right? 2.0 liters of this. So 2.0 is the volume, and 0.3 moles per liter is the molarity. from a 5 molar stock solution. So here is the other solution, 5 molar. I'm going to write 5 moles per liter. There's a blank in my table. So this is column V, row 2. I'm going to call this V sub 2, V2. Now I have all of my information organized, and I'm going to use this equation. So we're going to take M1 V1 equals M2 V2. And what are we solving for? We're looking for V2. So before I go plugging numbers in here, I'm going to rearrange the equation. So I need to divide by M2 to make it go away from this side. Because M2 over M2 is 1, multiplying by 1 doesn't change it, and you just got V2 over there. But to keep this equal, if I do it to one side, I have to do it to the other side. So I'm going to divide by M2 over here. Now I have my equation. V2 equals M1 V1 over M2. Now I'm going to carefully put my numbers in here. M1 is 0.3 moles per liter. V1 is 2.0 liters. M2 is 5 moles per liter. We have moles per liter in the numerator and moles per liter in the denominator, and so both of those will cancel out, and the volume is going to be in liters. And so we're going to get 0.3 times 2 divided by 5, same answer that we got from the thinking about it way, 0.12 liters. So does 0.12 liter really address what it tells us to do? Is that an answer to how would you prepare 2 liters of 0.3 molar KOH from 5 molar KOH? 0.12. Not really an answer. So the answer here would be that you would measure 0.12 liters of the 5 molar potassium hydroxide, and then you would add water to get the 2 liter volume that you need. So that's how you dilute something. It's a lot like making orange juice from concentrate. You measure out the solute, you add water till you get the right volume. Any questions? Let's do another example. Battery acid is 18 molar sulfuric acid. What volume of battery acid must be diluted with distilled water to prepare 1.00 liters of 0.50 molar sulfuric acid? Do you want to use the conceptual approach or the algebra? Algebra. So this is diluting. The word dilute is even in there. Diluting M1 V1 equals M2 V2. So we need to make a little table here and identify what these things are. 1 and 2, M and V. Battery acid is 18 molar sulfuric acid. Okay, so let's put that in for M. 18 moles per liter. Doesn't say anything about the volume. Let's go on and find the other numbers. 1 liter of 0.5. Those go together. So we're going to call that one 2. So 1 liter, that's a volume, and 0.5 moles per liter. I have a blank in my table. So this is V1. Everybody with me? So M1 V1 equals M2 V2. What are we solving for? V1, right? The one we don't know. So V1. So we'll rearrange this by dividing by M1. Those cancel out. We also have to do that on the other side. Volume 1 equals molarity 2, that's this guy right here, 0.5 moles per liter, times volume 2, 1.00 liters, divided by molarity 1, which is 18 moles per liter. 0.5 times 1 divided by 18. This should have only one significant figure, so 0.03 liters. Because moles per liter and moles per liter canceled out, and we've got liter left. 0.03 liters. Does that answer the question, what volume of battery acid must be diluted? Yeah. What volume? 0.03 liters. Here they're asking us for a specific number. The previous example was saying, prepare this, which is not a great question for a student. But I would say, how would you prepare? Make it into a real question. Any questions, comments?
Wouldn't it be 2 sig figs because it was 0.50?
Ooh, yes, thank you. I overlooked this 0. Shame on me. Yep, there was a 0 in there. Good catch. So this is not quite right. My calculator is saying 0.0277777777777. So 0.028. Thank you. Did I screw up anything else? Okay. Just trying to keep people on their toes.